Hi, I'm Dongping. In this talk, I'm going to introduce our work, Adaptive Channel Sparsity for Federated Learning under System Heterogeneity. Here is a quick preview of our work. Existing channel-sparse federated learning algorithms for tackling system heterogeneity prescribe fixed sparsity strategies for client models, while ignoring the potential detrimental effects raised by data heterogeneity. In this work, we propose federated learning with adaptive dropouts, namely the Flado algorithm. Flado differentiates itself from existing works in that it tailors an adaptive sparsity scheme for each client by a sparsity-driven trajectory alignment optimization. It aligns the client's gradient direction with the global model trajectory. Flado allows for collaboration on any parameter of a pair of client models if they have similar update directions, and it outperforms the compared baseline for system heterogeneity by a clear margin. In response to the privacy protection of data owners, the emergent legislation such as GDPR has imposed increasingly stringent restrictions on data collection, storage, and usage fees for centralized data analysis. This prompts the research on federated learning, where we can only send the model to server while keeping the private data locally. However, the local clients in federated learning may have different hardware configurations, which is known as system heterogeneity. For example, in a typical cross-device federated learning system, the client may occupy a wide spectrum of different hardwares, such as mobile phones, laptop, and desktop computers. The slowest device, also known as stragglers, only have very limited computing resources. They may slow down the training progress. To address the system heterogeneity, HeteroFL slices a submodel for each device to adapt to their computing capability. Similarly, Field applies order dropout to constrain the weights of the model to tailor the computation for each client. However, existing works use a straightforward sparsity scheme, which is mainly focused on tackling the system heterogeneity, but ignores the impact of local data distribution. They have two limitations. First, the coordinate-wise sparsity scheme ignores different data distribution among clients. As we can see later, this may cause conflicting gradient updates of their shared parameters. Second, the fixed sparsity scheme could hinder collaborative training. A simple example would be that a couple of devices need some neurons to collaborate, but these neurons may not exist in their client model. To address this issue, we propose to address the system and data heterogeneity in a holistic framework. Our first intuition is that in deep neural networks, neurons may specialize to distinct features, which can be supported by existing works. We hypothesize such a phenomenon also exists in federated learning. To validate the hypothesis, we synthesized 20 clients under MNIST training data, where every 2 clients receive the same digit to simulate a concept client shift. We observed that the clients allocated with the same digits shared similar update patterns, while different client pairs' update direction is quite dispersed. To summarize, we gained the insight that local gradient update is contingent on the local data distribution. This motivates us to further ask, can we concentrate training effort on neurons that specialize to the data distribution of local clients to foster collaborative training? We thus proposed federated learning with adaptive dropout. Here is a comparison of a proposed method Flado and the existing work Field. Flado differentiates itself from existing work in that it tailors an adaptive sparsity scheme for each client according to the local data distribution. However, designing adaptive channel sparsity for federated learning clients requires non-trivial endeavors. First, direct pruning channels would cause them to make low contribution later. Second, prescribing a fixed sparsity scheme to channels, as in existing work, can be suboptimal. Most importantly, data heterogeneity causes clients to specialize to train different neurons and could cancel each other in the global operation phase. To obtain the adaptive sparsity scheme, Flado adopts a sparsity-driven trajectory alignment. Specifically, it aligns the client gradient direction with the global model's trajectory under a constraint optimization objective. We establish an optimization problem under given flow budgets to solve dropout probabilities for each channel. and the dropout probabilities can be used in the next training round to specify local models. Intuitively, if a channel of a local client model has a conflicting update direction with a global model, its activation probability will be minimized, and we can even reach the optimized dropout probability to promote collaborative training of local clients. To reduce the computation cost of similarity calculation, we use fast join integer transform for dimension reduction. We compared Flado with existing works that also targets on system heterogeneity. The UniProv extension of federated dropout, hetero-FL, and fields. Flado attains consistent higher converged accuracy compared with those methods. Flado can converge 10 times faster than competing methods, giving a target accuracy, and it also drastically reduces the computation and communication costs. We evaluate Flado under varying data heterogeneity levels in federated learning. We empirically observe that Flado can tolerate aggressive data heterogeneity. We also empirically validate that Flado is highly elastic under different system heterogeneity levels. We provide further details and insights in our paper. Thanks for watching.